All right, everybody, I'm glad to be joined here by Eric Webb. You know him as Webber Weather on Twitter. I feature him often with tweets of interest every once in a while in my Hurricane Outlook and discussion videos. He's been on with me in the past talking about various and sundry topics related to my favorite topic, and that is the tropics. And so I thought it would be prudent to bring Eric back to talk about this four-letter combination of what makes up these interesting words, convectively coupled Kelvin wave. Exactly what that is. Hopefully we can discuss exactly what it is, at least approximately, right?
Yeah.
So all the way from somewhere in New Mexico, and he'll tell us exactly where, I welcome Eric Webb to Hurricane U. Thanks for joining me.
Thank you, Mark. I appreciate being on today. It's great. It's been busy weeks. This is a really nice reprieve.
They went from Raleigh at NC State playing hockey to Charlotte. Now you're in New Mexico. How'd that work?
Yeah, it's crazy. I went to Raleigh, Charlotte, and then I applied for this job as soon as I graduated. COVID kind of messed everything up, and I was kind of in limbo for several months.
Right.
But I was able to save a little bit of money to move over here, so that was great. And now I'm kind of like settled in and enjoying it. I do a lot of the same duties as a weather service forecaster, just for a different part of the government, let's say.
Gotcha. Well, I appreciate it. It's good to have you join us from the dry New Mexico climate.
Yeah.
It's very muggy back here in Wilmington, let me tell you.
Yeah, I actually went back there last week. I was at a wedding this past week, and it was a sauna. It was like a dew point in the 70s. I was like, I need to come back here because it's too muggy. So.
Well, speaking of, I guess, trying to segue into it, some mugginess, because we know these things do bring moisture with them. So that's slide into it.
Yeah.
This term, convectively coupled Kelvin wave, what is it and how is that different from the Madden-Julian oscillation? And how does this help and hinder tropical cyclone formation and so forth?
Oh, wow. Yeah, this is a good question. The first question's a really good one. Convectively coupled Kelvin waves MGO, there's actually, before I even get into it, there's actually, we tend to think of it, most of the research community thinks of it as sort of a spectrum, right? And so we tend to partition Kelvin waves. So back in the 80s, 90s, and 2000s, they developed these wave number frequency diagrams, and they identified parts of the diagram where there was a lot of power, a lot of activity, let's just say, on the diagram. And they separated those into parts, and part of it was a Kelvin and part of it was MJO. But really, there's honestly they're probably the two equatorial waves that there's debate in the community whether Kelvin waves are really MJOs or vice versa, But really, I guess if you want to, go into a bit more, a Kelvin wave is basically, a wave that propagates in the tropics much faster than the MJO typically does. It moves 10 to 15 meters per second. So it's moving pretty quick. So it's usually in and out of an area, usually 3, 4, 5 days. Usually it's typically what one will spend in one part of the globe. And you can, unlike MJO, where you can only usually have one MJO at a time on the globe, you can have 2 or 3 Kelvin waves operating at a time. And that's part of what separates it. And that's part of what makes it go a little bit faster, is because of that higher number of waves you fit into it. Right. Kelvin waves are really fascinating. Part of the thing that makes them really difficult to predict and sort of connect with Genesis is that Kelvin waves are, of large part, sort of the ignition for those, or the key that sort of that turns on the Kelvin engine comes from the extratropics. So these Rossby waves, these wave trains that come down from, say, the Arctic or the mid latitudes, they come down and they move into the tropics, and they change the winds, they change the stability in that area, and they change the amount of moisture, and that can set off a Kelvin wave, which then of course can in turn set off MJO. So that's part of what makes it hard to predict, is you have to actually get the Rossby wave propagation right, and we know in the mid latitudes getting the circulation right, even out 7-10 days, is hard. And so that's part of what actually makes it kind of difficult to forecast. So I guess then that leads to the question of why does it actually do? Well, Kelvin and MGO are pretty similar. Kelvin is sort of like the the biggest building block of NGO. The NGO is sort of like an ensembleized integration of a whole bunch of waves. Or some people also like to think of it as a Kelvin wave. An NGO wave is a Kelvin wave, but it's coupled to the extratropics a bit more strongly, so it moves a little bit more slowly.
Right.
So that's sort of in that perspective. But so in terms of like what they actually do for tropical cyclones, so Kelvin waves, they change the wind shear, right? When a Kelvin wave passes over by, you get a change in the upper level winds, and so that can change the tuts. That can change the amount of convection around.
So let me ask you this then: why the word Kelvin? Is that because of someone's name that discovered it or something? But I also hear you think about something being X amount of degrees Kelvin. Are those related?
Oh, well, no, it's actually named after this guy named Lord Kelvin.
Okay.
William Thomson, so he's a mathematician from Great Britain.
Gotcha.
That's what the scales are and the waves are named off of. He helped develop some of the temperature scales. So
it is related. Kelvin waves, Kelvin. We hear about something usually being very cold. I think.
Yeah. Yeah.
Kelvin. It's like, whoa! You hear that word Kelvin, it's got to mean something. So.
Got to mean something. So. Yeah.
All right, so these generally get started because of stuff going on in the mid-latitude. Is there a particular area where they get started, like a favorite area where they originate from, or is it random around the globe? And these are confined to the tropics, is that right?
Yeah, the Kelvin wave is confined to the tropics because outside of that you have Coriolis deflection. Sure. And it changes the force balances. So you technically don't have a Kelvin wave. You technically have something else. It starts behaving more like a Rossby wave. Gotcha. In that sense. But yeah, so is it random? It's part random and it's part, they're pretty evenly distributed unlike other types of waves. It really depends on the type of circulation pattern you have. If you have a certain phase of INSO, right? So for example, you have El Nino ongoing, you're going to have more frequent Kelvin waves where there's more frequent convection sort of in the means. Okay. So like what we're seeing here this year, right? We have Africa's really wet, right? And equatorial Atlantic is, and we're getting more frequent Kelvin activity in that area. So Kelvin waves in part are tied to tropical circulations, but they can get triggered by sort of those extratropical waves. And the circulation patterns that sort of radiate away from these convective masses that create these Rossby wave trains, they eventually circle back into the tropics and can trigger new Kelvin waves or suppress them. So sometimes you'll see a Kelvin wave actually get suppressed by a Rossby wave train and shut it off, or vice versa. So it's pretty fascinating. And then of course Kelvin waves, when they superimpose with the NGO, they get twice as strong. And they move much more slowly, and so that enhances the favorable phase. So that's part of what makes having NGO in place favorable as well, is because it lengthens the time that Kelvin wave is typically in place, and so it makes that good environment last much longer. And so that's where a part of that comes from.
Well, how do you see a Kelvin wave? How do you know that it's there? What are the observational methods?
Yeah. So the observational methods, one of the most common ones is to use bandpass filtering. Basically look for sort of a certain part of the spectra where waves are within, say, that are of certain a certain length and that are moving across that some given point or given area in space in some certain time interval. So we search for typically, I think it's on the order of a few weeks or so. It's usually on the order of 1 to 2 weeks, roughly, give or take. NGO is a bit more broader. It's like 30 to 120. Of course, that also doesn't mean that we don't have waves that don't exist between, say, 2 to 3 weeks in a month. There are waves that do. We're just not searching for it. We're kind of like, we basically, you can kind of think of our methods of searching for Kelvin waves like a flashlight in the dark. And we're only just looking for that type of wave. It doesn't mean something else doesn't exist.
Gotcha.
Because it's not there in a diagram. We're just not looking for it. And so there's actually a whole spectra of waves, but bandpass filtering is typically one of the ways. You could also kind of derive it if you look at, say, like a 5, 7 day or 10 day averages. It's basically kind of what that is. is you kind of look at a collection of 5, 7, 10-day average fields, and you look for movement across that space and time, and that can help you detect the Kelvin wave. And so that's kind of how they usually go about it. I've been trying to learn how to do that and try to code up some of these things myself, because I'm just curious. I like to look at past things, like, I like to look at what the Kelvin wave or equatorial waves were doing, say in the 90s or 2000s when a certain TC was going on. So, I'm trying to learn how to do that. I'm reading a lot of papers on it lately to try to just grapple with it. But that's basically how it works in a nutshell. So
the Kelvin wave brings different parts here of favorability and better setup for wind shear. There's less shear. There's more moisture associated with them. And that's my understanding that they also bring a little bit of a westerly wind component down at the lower levels and kind of help with vorticity. It's kind of like this favorable incubator kind of thing that moves kind of in and of itself. And so that's so what does the convectively coupled part mean? We've identified the Kelvin, and who that is. Now, how about moving along? And we know what wave is. Everybody can picture a wave, and the atmosphere has waves in it. It makes sense. What about this convectively coupled part?
The convectively coupled part's a really interesting part, and it's where this sort of the simple dynamics kind of get tossed out the window, and you start including moisture and whatnot. And so basically, the difference really between, say, like a dry, fast Kelvin wave and a slow, moist one is the moist one, for one thing, is going to move slower, but it's going to have convection and moist convection associated with it because of the wind, the changes in the winds and the circulation that come with the Kelvin wave. And so you mentioned a lot of those things, right? So there's a change in the shear, right? You get the change after a Kelvin wave passes by. You get an enhanced feed of upper level easterlies that feed from the convection that's associated with the Kelvin wave, and that lowers the wind shear in the Atlantic. It actually increases the wind shear in the East Atlantic because the shear is easterly out there and right next to the African coast. And so actually, but overall, it's a decrease in the shear.
Right.
And the decrease in shear is important because it also changes the way the Rossby waves propagate into the Atlantic. And so behind that area of easterlies, right? So a Rossby wave is a westward moving wave.
Right.
And if this westward moving wave comes into this easterly shear zone, it's going to get sheared apart faster. It's going to have a harder time coming into the tropics. That, and there's more convection going on, so you're creating high pressure loss. So you're moistening the atmosphere and you're creating this upper level area of divergence and heights. And those two things are what actually help. For example, they degrade tuts. So behind a Kelvin wave, you're going to see tut activity usually drop because it changes.
Is that tropical upper tropospheric trough?
Yeah. Yeah.
So those you said would be behind the Kelvin wave.
Mm-hmm. Yeah, and ahead of the Kelvin wave, you'll have the anomalous westerly, so you get an increase in shear. And it's almost like, let's say you're at an airport and you have the moving sidewalks, right? It'd be like you trying to switch sidewalks and you're moving in one direction, the other one's going the other way, and you're trying to switch the other one, you're likely going to fall or you're going to stumble, right? Versus on the other side of the front side of the Kelvin wave, where you have anomalous westerly winds out in front of that convection, it actually allows those Rossby waves to filter through that layer. And so basically, if you had two moving sidewalks in the same direction and you tried to sidestep across them, it's much
more smooth transition. Okay.
Yep, and that's what helps actually increase the shear, and it also increases the waves. And of course, it being dry in the column ahead of the wave, it's usually driest right before it comes, and that usually creates cyclones in the upper troposphere, and that's usually not favorable because again, it's associated with wind shear and there's less moisture. And that's the other thing is that why the Kelvin wave is most favorable after it is because after it's already passed, that's when you have the most moisture right in the atmosphere. That's sort of left over behind it, and so you're usually the most moist too, in that sense as well. And then you talked about the cyclonic shear vorticity, so the lower level winds. The big thing we're seeing with this Elsa, the hardest thing it's having trouble with is closing off the westerlies on the south side. Right. The Kelvin wave can help with that. because it can create within its own envelope a layer of westerlies that can allow the storm to sort of spin up in these waves.
Right.
And so that's all of those things together kind of what make the Kelvin wave what it is. And it usually lasts 3, 4, 5 days, several days usually. And it's and they typically, you can have 2 or 3 across the tropics at a time.
Right.
So, and they can move through NJOs and all kinds of things. It's pretty fascinating.
Sort of start systems off. Like, did Elsa get a kick from a Kelvin wave to kind of help it? I heard mention of that. And it hasn't even reached the area where a Kelvin wave is or something like that. You read a lot of stuff on Twitter. I think I saw that at some point. So was there a CCKW involved in Elsa's genesis over the last couple of days?
Yeah, there actually was. And I'll share my screen and show that. And so in here, and so I can actually go, this is on Carl Schreck's site. And this is, he also went to NC State and he works for NCEI. So he does really a lot of great work. It's another site I use along with Dr. Ventress's that I think most people are really familiar with. So the green colors here, this is velocity potential, which measures basically the irrotational or part of the flow. Basically, if you just measure divergence, say in the tropics, there's going to be a component even down there that's going to have some rotation to it.
Right. So
basically it takes that out and says, okay, what's the part that's purely diverging, spreading out? And so the green colors are where you see divergence. Browns are where you have sinking. And then the interesting part is here down on the bottom, you have these things. So the black is the NJO, right? I think some of your viewers and listeners are familiar with that. You have this pink, which is low frequency. So you can think of that like as INSO, for example. So INSO would be like a low frequency standing, sort of like a standing wave. And the blue is the Kelvin wave, and the red is the equatorial velocity wave, which we probably thought we don't have time to talk about today. But you can see as Elsa formed here, which is this E and this June 25th to July 1st part of the diagram, there's this big green blob of negative velocity potential that came across the wave. And that occurred and within the days as it was coming off of the coast of Africa. And so it allowed the wave to sort of get convectively active. And it lowered the shear, increased the moisture, give it some enhanced westerly winds so it could kind of close off its circulation. All of that came together and allowed it to sort of develop out there. And then the other thing was the seasonal state is really favorable. Right? This Atlantic Nino that a lot of people like to talk about that's ongoing. And so it's kind of all those things added together that's really given us this. And what was fascinating when I actually looked at this particular Kelvin wave, you can actually see, this doesn't happen quite often, but this particular Kelvin wave, you can see Elsa here, this little E right here on this part of the diagram near July 1st, right? This is basically telling you when the storm's formed. And if you trace this blue contour, right, which is the Kelvin part, right, this blue, it actually extends and it goes all the way back to about late May, June in the Pacific. So this particular Kelvin wave has actually transited the global tropics more than once already, and it came back. So it's actually pretty fascinating sometimes how you can see things that sort of evolve over periods of weeks. And this is sometimes what can happen. Sometimes a Kelvin wave can sometimes just stay together for weeks and weeks and weeks. And so it's pretty cool how it works. And so so it's pretty fascinating.
So does the Kelvin wave then potentially sort of morph into a Madden-Julian oscillation?
It certainly can, yeah, and usually that tends to happen over the Indian Ocean if it usually occurs. That's where your sea surface temperatures are really, really warm. It's in that warm pool area, right? And that's usually where you get more convection in the wave, and you get the waves usually start to slow down a bit as they go over that part of the globe, because there's lots of areas for convection. And of course, the other thing is that the waves aren't quite frequently as breaking into the Indian Ocean. So that's one of the things that actually drives the phase speed. So like, how does a Kelvin wave, like how do you know how fast it's moving, right? Or NJO, because that's often important, right? When we're looking at an NJO, we're saying, when is it going to get here? Yeah. A lot of that's actually dependent on how fast the extratropical jet streams are going. And those actually push the wave along. And so in that part of the world, it's actually the jet streams are usually a little bit slower. Whereas in the Western Hemisphere, we have more waves going into the tropical areas. We have less warm SSTs. Our SSTs are nothing like they are back there, and we have more land. And so it interrupts the moisture processes with MJO and sort of gives it more speed, and it behaves more like a Kelvin wave, usually in our part of the world. So yes, that's usually what will happen is a Kelvin wave will come over Africa, Western Hemisphere, hit the Indian Ocean, and then develop, and then move across the global tropics into the Pacific. It's that part going from Kelvin to MJO, and then that part that when you cross from Indian Ocean to Pacific, those are the hardest parts to forecast. Usually once an MJO is in the Pacific and it's advancing toward the Western Hemisphere, we usually have a pretty good sense of that. But it's in that part of the globe, things in those situations that can be pretty tenuous. Models usually really struggle pretty hard over there.
Well, when we hear about a suppressed phase of the Kelvin wave, what does that mean?
It just means that, you have the opposite conditions going on. So you have large-scale subsidence warming aloft, right behind the wave. You tend to have more sunshine. So it's sort of like a recovery period, right? You can think of the Kelvin wave. It's sort of like if you're jogging and you're jogging for 5 minutes, then you take a break, start walking for 5 minutes, and then you pick up jogging. So that suppressed phase is sort of like, you're sort of walking, or you're taking a brief break, and then you're in an enhanced phase, you're coming back to it. What's pretty interesting too about how these waves work, and so the suppressed and the enhanced phase areas aren't usually equal over the globe, which is pretty interesting actually. The enhanced phase, the spatial area of the enhanced phase is usually smaller than the suppressed phase. The suppressed phase encompasses more area. It's pretty fascinating because that has a lot to do with the differential in density between dry and moist air. Right. So it's actually, that's where it's coming from. So you'll see the enhanced phase will be actually smaller in scale than the dryness. So most areas of the globe are actually in the suppressed phase more often than not. And so it also like the enhanced phase, it usually takes several days across the tropics. And during that phase, you're going to get drier air. You get Saharan air layer, dust outbreaks, right, with all that dry air, and it helps. And then, of course, you start getting Rossby waves that start breaking back into the tropics because now you're increasing the westerlies again aloft because you're getting away from that convectively enhanced phase. So it's all pretty fascinating how everything sort of works together.
Yeah, agreed. I mean, we see it, especially those 4 letters, CCKW. People toss it out there. And it's really hard to visualize, though, to conceptualize and explain to people, well, what exactly is that? And it's one of those sort of amorphic things that you can look at, those diagrams, you can look at them, you know exactly what you're looking at. But to the common person, at the end of the day, they hear it, they see it, and charts are made for it, and it's discussed on message boards and social media. And then what does it mean at the end of the day? Well, it can help to sort of supercharge or at least jumpstart something in the tropics. And in the case of Elsa, I guess that's exactly what happened. But it's part of the overall equation. It's not the thing. It's not this started because of a Kelvin wave. I mean, there's other things in the background going on. It's very complex at the end of the day.
Yeah, it's very complex. I mean, I was reading a paper. So my advisor, I think I also shared social media. My advisor at NC State was Dr. Ayer. He was actually specialized in tropical waves and dynamics. That's part of the reason why I got really invested into this stuff, because he knew a lot about it and he shared a lot of his knowledge with me about it. And so one of the things, for example, that's separate from Kelvin MJO waves, sort of independent, is sort of you have this upstream wave dispersion. So you know how in the extratropics, these wave packets will move from, say, the recurving typhoon. Everyone sort of more people will kind of understand that. And the waves propagate downstream. That wave train moves along, right? Well, in the case of easterly waves, there's also wave trains, but they don't tend to move as frequently westward, say, or have a single phase direction. But they tend to move actually retrograde really slowly, usually on the order of 3 or 4 meters per second to the east. And so what we actually had in this particular case is we had Invest 95L that died. It was a big wave that came off.
Right.
What could have happened in that case, even without, not without, but somewhat independent of it, is you had sort of this energy getting transferred from that wave to the one right behind it. And that happens usually really, really slowly, much more slowly than the Kelvin wave. That's another process that complicates the whole matter. So like you said, it gets pretty complicated pretty quickly when you start even trying to think even beyond those things. It just gets super complex.
It does. And I mean, so when we think about tropical cyclogenesis, how much of this is getting incorporated into the prediction of when systems are going to spin up? Because, you know, in the deep tropics, I think it's a little easier. You get these large pieces of energy that come off, and, you know, they're a little bit easier to identify. And since these Kelvin waves are going to be mostly down in the tropics, we don't see them affect something like Imelda a couple of years ago in the Gulf. That's not really going to affect that. Is that too far north? Or Danny, which came from, I think, an upper level system that eventually worked its way down, if I recall. Those Kelvin waves aren't going to reach up into the subtropics and kickstart anything, you know, because Danny, we didn't get a PTC designation for.
Yeah.
We did for Imelda, and we certainly did for Elsa. And so, you know, you can look at some of these, which ones have fingerprints of a convectively coupled Kelvin wave on them, which were, you know what I mean? It's like you start, it gets crazy really, really fast.
Crazy really quick.
So I guess to try to summarize, well, what exactly is your question, Mark? In the development phases, what we call tropical cyclogenesis, you know, and what I'm getting at is, are the computer models, the global models, able to factor these Kelvin waves in, or are they just kind of there and it's coincidental? Is there a way to factor them in and kind of tell it? You know what I mean? Like, it's,
yeah.
We wonder why some stuff develops and why others don't.
Yeah, it's pretty fascinating. So as we mentioned earlier, so accurate depiction of the Kelvin wave also requires accurate depiction of the extratropical circulation, because that is what sort of helps force them along and or develop or suppress Kelvin waves. And so that's sort of part of the limit. Part of the other limit is they move so quickly and they have a lifespan. They're typically only a few weeks lived, typically a few to several weeks, versus MJO, which can take months, right? And it can last for heck, half a year or more. You can have a couple pulses and you go, man, we had one in January and we've only had two, you know, and it's June, right? So MJO is a lot more slower. So there's a bit less predictability from the fact that it just has a shorter lifespan, and it's typically smaller than MJO. That's the other thing, is the models are usually better simulated at bigger things, right? The bigger things take longer for those errors to kind of grow upscale and affect it and affect the MJO, versus Kelvin wave, which is a little bit smaller, a little bit harder to predict, has a bit more dependencies on what's happening in the extratropics and whatnot. And so that sort of shrinks our predictability. And then, of course, you have to deal with a coupled convective part, right? Models have convective parameterization schemes, and so those don't adequately resolve convection. And in the case of the GFS on ECMWF, there was some interesting work in an AMS conference that showed, think about after day 7 or 8 or so, they typically kind of lose a lot of the signatures. So they're really not accounting for them after the medium range. And so that's part of the reason why it kind of makes tropical predictions so hard, is because we can't really forecast the subseasonal parts of it quite well yet. Much less once we get that, then we have to forecast these mesoscale dynamics. And our best observations are satellites. We don't really have, you know, I was a big fan of the Global Hawk. I know you guys remembered that piece of machinery. It was great because it, for example, Edouard, which was way out in the North Atlantic, it was in 2014. It got sampled and upgraded to category, I think it was a 3, if I remember correctly, because of the Global Hawk mission. And those drones are something I think we should really use, because then it's less dangerous for the people there, and you can fly them lower to the surface. You don't have to, you know, extrapolate the numbers as much like the aircraft does. So like what you guys see on Tropical Tidbits one, that's all extrapolated except with the SONS. So you don't have to do that as much with the drone. You can fly it really, really close to the ground and not have to worry about people being in danger. And
you can fly them up to 60,000 feet as well. I mean, the Global Hawk. So, I mean, it just shows you how complex all of this is and the limitations. I think it really still exposes the limitations. As far as we have come, we still have a long way to go. And it's a relatively new concept that I've seen on social media over the last 5 or 6 years, even though I'm sure the phenomenon has been studied and observed and talked about for much longer than that. Now these things kind of come out and we see them talked about more and more, thanks to people like you and Michael Ventris, Dr. Ventris up there in Massachusetts. And So I just thought it'd be interesting, even though it's not easily explainable, that we at least opened up the can, so to speak, look inside and say, okay, well, that's interesting. There's a lot of soup to nuts in there, so to speak, of mixed stuff. It's not really, the atmosphere is complex, and the Kelvin waves are certainly part of that.
Yeah,
It's sum it up. So let me just ask you this last question, and I'll let you go. Where does the research go from here? Do you know? Is that an easy answer? Like, what's the future of studying Kelvin waves and how they can help, especially with tropical cyclogenesis or just rainfall patterns in the tropics?
Yeah, I think one part would be getting better data sets and better, better analyses. Like some of these wave frequency spectra are based on older analyses that ended in the 2010s. So we have a lot of new data that's come out since then that would certainly help. For example, Africa being pretty wet is something we haven't really seen in those earlier parts, and so maybe that's changing the characteristics of the waves. Also just understanding a lot of these convective scale processes that occurred. So understanding, and I guess I could maybe briefly segue into this, I guess, real quick. If I don't know if we have time, but
minutes, absolutely.
Yeah. So let's segue into this. So I guess sort of kind of leaning on that, but sort of getting this tropical formation process and kind of going into more of a what drives the formation of these tropical disturbances, sort of starting at the smallest scales, right? Because that's really where it's going to help us, because those errors grow upscale and they eventually project onto these Kelvin MJO waves. So it's the first part is figuring out, or part of it is figuring out what happens at the smallest scales, right? So how do these systems form? And one really smart individual, med student, asked me, hey, why do these mid-level centers, we all love the tropics, right? We all track these systems. Why do we see these mid-level vortices on satellite? You can say, oh, this wave's got all this rotation. It's in the mid-levels. It looks great. Look at all that spin. Then the recon plane gets in there and it's like, oh, there's nothing there. Right. So the question that becomes, why is that happening, right? So why are we seeing these mid-level centers form usually first, not always, but usually before the surface cycle? So there's actually a couple important processes that happen here. One of them is this latent heating distribution differential across the depth of the cloud. And so, as you guys probably are aware, these clouds in the tropics are really, really tall. And at the tops of the clouds, it gets really, really cold, right? And so we have snow and all these different kinds of different types of water up there. And the conversion of that gaseous phase, that vapor that comes off the ocean, goes up into the cloud, and it condenses and it turns into either snowflakes. That's would be called deposition, because it's going from a gas to a solid, or if it's a liquid already and it gets pushed up, it freezes. That releases latent heating up in the upper parts of the cloud above the freezing level or melting layer. And then below that, right, we have these snowflakes falling underneath it, right? So we have these snowflakes, they're getting melting of these snowflakes as they fall to the warmer parts of the cloud. You also have evaporation below the cloud, because it's not 100% RH, right? There's usually a little bit of room for some evaporation, and you got the ocean too that's contributing to it. So you get a cooling below that. That process actually creates an area of low pressure between that area of warming and cooling. Because aloft, the warm air expands and it pushes down these pressure surfaces from aloft. It pushes the lower pressure down from aloft, and the cool air, it sinks and compresses, so it encourages that warmer air, or that lower pressure from aloft, to come down a bit. And so this creates this cyclone. It's in the mid-levels.
Right.
And so it's from these processes. There were some really good papers that came out a couple of years ago that actually showed that in hurricanes, you wouldn't think about it. It's too warm in the tropics. Who cares about snow, right? Well, snow and grapple and ice, these are all important because they help spin up these mid-level vortices. So Elsa, at one time, this process was a pretty significant one in contributing to the spin up of the vortex.
Wow.
So it's a very intuitive one, right? So you're just thinking about the differences in how the latent heating is distributed across the cloud. And this other one is a little bit more tenuous, but I would say this also has some conceptual application. So right at the surface, right, we think about this air rises up into this tropical storms, right, in hurricanes. Well, right at the surface, like right at the ground level, air is starting from zero, right? So it's kind of like you're at a red light, you're sitting at a red light and you have to accelerate upwards. And so it takes time for those parts to accelerate upwards, but they take that warm, moist air with them and they accelerate and they actually pick up speed as they go through the low and mid-level parts of the cloud.
Right.
And as they do so, they deposit latent heating. Well, what happens is the difference, the speed difference, which the speed, I've over-exaggerated this. This is actually kind of not necessarily accurate at all. The vertical speeds are pretty low, but this is a process that does occur. And the faster moving winds that are pushing more vapor aloft, higher up in the clouds, say, in the low to mid levels, versus, say, here at the ground where you're having evaporation off the ocean, that's occurring, say, underneath this developing cloud. And so you get this latent heat release that occurs faster in one part of the cloud because the winds are moving more vapor into that area much more quickly. So this is another process that also contributes to the development of this mid-level vortex. And that's kind of, like I said, so these processes together, and of course, there's the other one that Manuel in the 80s talked about, and this is kind of related to it, as stratiform. So you could think of stratiform as sort of an extension of this process. So these all together give us that mid-level vortex that develops first when we see on satellite. Yeah. But to get the surface vortex, this is one of the biggest questions in tropical research, and I think that's one of the big problems we have with forecasting systems like Elsa is what happens from this phase right here. We have this mid-level vortex that's formed in the cloud, right, because of these processes, to getting the surface cyclone. What the heck's happening between there? There's a lot of debate. There's not really much of a consensus on it, and so we're still kind of left scratching our heads. So it's really, really complicated, and I think these things too, resolving these things can really help with Kelvin Waves, because all these errors grow of scale, and it can only take several days, and all of a sudden you not being, let's say if your model doesn't show snow or grapple or ice correctly in a cloud, it can actually affect the spin up of a vortex, even though it's so warm. You're like, oh, who cares? Again, who cares about snow? But it actually, does permeate into all those things. So yeah, I didn't mean to take too much of your time, but I think that's kind of, starting at kind of the small scales and starting to kind of grow up. And I think too, it'd be great, especially for us in the Atlantic, if we had a better observing network over Africa. There's so much. I just feel really, really bad for a lot of those people there that have to deal with the turmoil that's going on constantly on that continent. And so that's another thing that really hampers us here in the Atlantic.
Yeah, the observations. That's the first part of research. I mean, without
exactly.
Right. Very interesting. I mean, this is I think the point too is, again, that word complex. There's a lot more to it. No, I mean, so much more. Well, I appreciate this. This is nice. We'll think of some other interesting topics to bring you back and discuss. Maybe the desert monsoon and how tropical cyclones get involved with that, because that's a very high interest area of mine. I look at it as when you get a tropical cyclone out there, you kind of speed up geologic time, and things happen real fast over just a few days, and then the cyclone leaves, the leftovers leave, and everything goes back to the way it was. And I think that's an interesting situation, where that's an arid climate. It's amazing out there. And then you get a tropical cyclone. And now that you live out there, close to it anyway, in New Mexico, it piques my interest about that even more. I'm eagerly anticipating coming up like a Norbert or an Odile or a Rosa. It's been a while. I was out there in 2018 for Rosa. So we'll talk about that stuff again, I'm sure.
Yeah, it'd be great. I'd love to be on. I really enjoyed. I really just thank you for giving me the time to come on. As I know you have a busy work schedule. I know
it's deep. It is definitely deep stuff here, but I like stuff that gets in depth, and that's what this is all about here. This little series I've been doing for a couple of years, this Hurricane U, just a little peek into the world of the academic side of tropical stuff, instead of all the flashy, interesting, 10,000 views of a video or 26,000 shares of an image or whatever. There's a lot behind that, And this is a glimpse into that world. So I appreciate it very much, Eric.
Thank you so much for your time. I really enjoyed talking with you. And like I said, I'd love to talk more about the monsoon at some point. I'm trying to get acquainted with that here. That's like, man.